Thank you. I'd like to begin by thanking the organizers for giving me the chance to speak here, and thank you for coming to my talk. Today, I'd like to tell you about some work that I've done together with my wonderful collaborators, Inbal Livni Navon and Mary Wooders. So I'm going to begin by setting the context so you know where our work fits in the grand scheme of things. As I'm sure you're all aware, having listened to enough talks by now, we need some form of quantum error correction to build scalable quantum computers. But error correction is a resource-intensive process, so the name of the game in error correction research is to find the most efficient way that we can perform quantum error correction. Over the past decade or so, quantum LDPC codes have been identified as one path to performing scalable quantum error correction. And as we're trying to implement these codes, one important component that we need to figure out is what's called a decoding algorithm. A decoding algorithm helps us quickly identify errors and correct them. So the purpose of my talk today is to introduce to you a new decoding algorithm that applies to a specific class of quantum LDPC codes. So I'm going to start with the basics. I'll quickly get some boilerplate information out of the way. So an NKD stabilizer code, that's going to be the focus of my talk today, is denoted here using H. It's a subspace of the 2 to the n dimensional subspace complex Euclidean space that's associated with n qubits. And it's a way for us to encode k qubits into a space of n qubits. So those are the parameters n, k, and d. And how do we specify this code? We do so using m-independent Pauli operators that also commute. And I specify my code space as a function of this set of operators. All of my states in my code space are left invariant under the action of these stabilizer generators. I'm going to be using diagrammatic notation to illustrate objects in my talk. And in particular, I'm going to use this sort of bipartite graph to represent my quantum LDPC codes, just as we heard in the previous talk. The elements of this graph are these square nodes, these circular nodes which represent qubits, and the square nodes which represent my stabilizer generators. And if a qubit is in the support of a stabilizer, then I'm going to draw a line between, I'm going to draw an edge between these two vertices. So if the code, the state is in the code, then when I measure these stabilizer operators, then I'm going to get a +1 outcome for all of my operators. And if there's an error that's detected, at least one of these stabilizer generators is not going to return a +1 outcome. In this case, I'm going to say that the generator is unsatisfied, or unsat for short. And on a related note, this final parameter d is the weight of the smallest undetectable error. So this is a measure of the robustness of our code. What is an LDPC code? An LDPC code is one stabilizer code where when we consider this graph, all of our stabilizer generator nodes have constant degree, or in other words, every generator only acts on a constant number of qubits. And furthermore, every qubit is only going to be involved in a constant number of stabilizer generators. So the degree of both of these elements, the stabilizers as well as my qubits, is a constant. Why is this interesting? We've already heard from multiple experimental implementations today, but just to drive the point home, LDPC codes are interesting because it's easy for us to engineer circuits where qubits only need to talk to a constant number of other qubits. And from the point of view of fault tolerance, this is also useful because this limits errors from spreading. There's only a limited number of paths for errors to go from one qubit to another. And more recently, it's been pointed out that because these codes have constant rate, you can also construct schemes for performing fault-tolerant error correction such that the cost of encoding a logical qubit, namely this ratio n over k, remains a constant no matter how large you make your circuit. So this feeds into this narrative of efficiency that we talked about earlier. So this is motivating the why behind LDPC codes. And I'm going to soon dive into a particular construction, but before doing so, I'm going to have to define for you what it means to have a certain type of graph called an expander. I apologize, there's going to be a slew of words that's coming at you, but it's a fairly simple concept. So let's get started. I'm going to be considering a bipartite graph. So that means that my graph is divided into two portions, and these two portions are going to be given the labels V and C. The V-type nodes are going to be denoted using circular nodes, the C-type using square nodes. And this is bipartite in that edges only run from the circle to the square-type nodes, never between circle and circle. It's unbalanced in that the number of V-type nodes is greater than the number of C-type nodes. And I'm going to say that it's biregular if all of the elements, all of my circular nodes have constant degree delta V, and all of my square nodes have constant degree delta C. So we have a bipartite, unbalanced, biregular graph. And we are going to be considering what are called alpha epsilon expanders, which expand from V to C. And what does this mean? If we were to consider any subset of vertices in my graph, so some subset S that I've highlighted here in orange, if the subset is small enough, then its neighborhood, here denoted using gamma, so some set of edges on the other side, is going to obey a certain property. What is this property? So in its heart of hearts, an expander wants to be sort of tree-like. You want all of your outgoing edges from any set that you consider to go out and meet new vertices. But of course, this can't happen for every possible subset because then you just have a bunch of disconnected islands. Right? So if you were to consider a set of size S, the number of edges that you'd have outgoing ideally is delta V times S. And in an expander, you settle for almost that. Only an epsilon fraction of your outgoing edges are going to collide onto vertices. The rest of them are going to go out and meet new neighbors. So that's what it means to have an alpha epsilon expander. So the alpha tells you how large of a subset you can consider, and the epsilon bounds the number of collisions. And this graph is said to be a bidirectional expander if it expands not only from V to C, but also from C to V. And these are the sorts of graphs that I'm going to be interested in today. Okay, so we're going to use these sorts of bidirectional expanders to construct what are called quantum expander codes. And we just heard about them in the previous talk, but let me quickly explain to you again, because certain parts of the structure are going to be important for me to explain to you how the decoding algorithm works. So these quantum expander codes are a particular instance of this hypergraph product code that we just heard about. And in particular, they were introduced by Leverrier, Tillich, and Seymour in 2015. And how does it work? This construction is this meat grinder which accepts as input 2 copies of this bidirectional expander. And it's going to spit out one quantum code. In particular, if the 2 input graphs are sparse, meaning they have constant degree, then the output is going to correspond to a quantum LDPC code. And in particular, if we have this bidirectional expansion for sufficiently small epsilon, we are guaranteed that 1, the rate of the code is a constant. So remember that this is a property that we wanted for building efficient quantum circuits. We wanted a constant rate. And second, we also have a lower bound on the distance. We can prove that the distance scales in proportion to the square root of the block size. So I'm going to state this fact without proving it, but this is one of the reasons that this construction is useful. So how does it work? There's usually 2 pictures that we use when describing the hypergraph product code, and one of them is what I call the quadrants view. The hypergraph product code, or this quantum expander code, is really constructed by considering the Cartesian product of 2 bipartite graphs. So what are the elements in my graph? They were these V and C type vertices. And when you consider the Cartesian product, you can consider V times V, C times V, C times C, or V times C. And each of these resulting objects now have to be associated with an element in my quantum graph. So when you have 2 circles or 2 squares, this quadrant and that quadrant right here, those are going to be associated with qubits. And if I were to consider the opposite quadrants, well, you might guess that these are going to be associated with my quantum stabilizers. And I'm just going to choose, for consistency, the V times C. So this quadrant right here is going to be my X-type parity checks. And the opposite, the C times V, is going to correspond to my Z-type parity checks. Okay, and for the sake of illustration, I've included exactly 1 edge from each of my component graphs. And you can see that if I were to look at this edge and the resulting nodes that emerge from the product of, say, this check and that variable. So if I were to look here, this edge is going to be inherited by the resulting quantum construction. And every pair of edges, one in each graph, is going to result in a 4-cycle in the resulting quantum code. And this is important because this is what guarantees for you the commutation relations that are required to guarantee a good quantum code. In other words, if I were to consider an X-type stabilizer here and a Z-type stabilizer there, anytime the X and Z meet on a VV-type qubit, they're also going to meet on a CC-type qubit. So they always meet in pairs, and this orthogonality relation that you need to define good quantum codes is always guaranteed. Okay, so the next picture that's going to be useful when talking about hypergraph product codes is what's called a local view. And a local view is what you might see if you were to sit on a Z-type stabilizer and look outward. You see the VV-type neighbors, and so this pair for this square node, for example, the Z-type stabilizer is associated with the pair C1V2, and its VV-type neighbors are the neighbors of C1 times V2, and its CC-type neighbors are C1 times V2. And all of the parity checks that you get here are gamma C1 times gamma V2, or remember I used gamma for the neighborhood, so it's a neighborhood of one times the neighborhood of the other. So you get this square. Why is this useful? Right, so I just said this. It's useful because it highlights some properties of the hypergraph product that are not otherwise immediately obvious. For instance, if I were to have an error, one here and one there on these two qubits, a Z-type error specifically, then this X-type stabilizer is going to be turned off. So there's this interference effect, which then is going to make it complicated to find out exactly where an error has occurred. Okay, so I will return to this when talking about my decoding algorithm. Okay, so know your enemy. What exactly are we trying to battle against? We're trying to correct against poly errors, but typically when we start by thinking about error models for quantum error correction, what are the two models that we consider? The simplest one is the erasure. And in the erasure model, the qubit is, the state is no longer in the span of the two-level system that we start with. Instead, it's escaped, perhaps it's leaked, and we denote this using a special symbol, perp. And erasures are great because we can locate exactly where they've happened. We can perform a measurement using a POVM to project onto this two-level space or not. And if not, we know exactly where they've happened. And because of this, it's easy to correct. We can always guarantee that there exists a polynomial time algorithm to decode against erasure type errors. Poly errors are, of course, the types of errors that are more difficult to correct. They are the analogs of bit flips in the classical setting. And in particular, because these are CSS codes, meaning that the stabilizers are only ever X-type or only ever Z-type, we can correct these errors separately. So we can correct only X-type errors using the Z stabilizers, only Z-type errors using the X stabilizers, and that allows us to correct any type of poly error. So for my talk today, I'm only going to tell you how to deal with Z errors, and because the structure of these two codes, the X and the Z parts are the same, you know how to correct X errors as well. And because I'm using the X-type stabilizers to correct against errors, I might later refer to these objects as the parity checks, just to drive home the point that I'm correcting the Z errors. Okay, so what's the objective today? The objective is, if we start with these poly errors, which are difficult to correct, is it possible for us to convert them into this scenario where it's easy to correct? Namely, can we convert a poly error to an erasure error? And the answer is going to be yes. We generalize what's called Wiedemann's algorithm for classical codes, and here's going to be an informal version of our main statement, where we say that if you're going to give us an error E on a hypergraph product code, we are going to we have a new subroutine. It's called small set find. I'll explain why it's called that in a second. But small set find is going to return for you an envelope that contains the error. So you're going to have this green blob that is sure to contain the error. And then what you can then do is delete all of the portions that are within these green blobs, replace them with erasures, and then run your favorite erasure decoding algorithm, and you're done. So that's how this algorithm works. Okay, so highlights why should you care. You should care because first off, this is a new decoding algorithm that's different from the previous decoding algorithm that could provably correct errors, namely small set flip. Generalizations of decoding algorithms that now work for these good LDPC codes that you might have heard of generalize small set flip. So this is a fundamentally different class of object. Second, small set find is a linear time algorithm. So if you're worried about efficiency, this is something that you would care about. And most importantly, this algorithm can correct errors of size up to basically d over 2. So you can up to asymptotic parameters. This is optimal. Now, of course, the entire decoding algorithm is not linear time because we do not have, surprisingly, we don't have linear time decoding algorithms to correct erasure errors for even for hypergraph product codes. So to the best of my knowledge, even if you were to use these generic erasure type decoding algorithms of size n cubed, then all in all, you're still going to be left with an efficient algorithm to correct from any poly error, but this part still needs to be sorted out. For it to be entirely linear time, we need an erasure decoding algorithm that can recover in linear time. Okay, whoops. Okay, so now to tell you exactly how this algorithm works. By the way, this find, the name for this algorithm comes from a subroutine in Biedermann's algorithm, which is called find. And I'm now going to tell you why it has this prefix small set. So how does this algorithm work? It iteratively maintains this envelope L and a set of suspicious parity checks R. And at every iteration, it's going to update both L and R. And so initially, it's going to say that it doesn't know what the set of corrupted qubits are, but the set of suspicious parity checks are certainly the unsatisfied parity checks, because you're sure that these are adjacent to some errors. And how this algorithm is going to work is it's going to consider small sets F that are inside the support of a Z-type stabilizer. So you're going to begin by considering Z-type stabilizers, and the set F in this example that I've used to illustrate how this algorithm works, the qubits are highlighted in orange. And when is this suspicious? Well, there's a score function to tell you whether or not this is suspicious. This set F is suspicious. It's going to first, so let me tell you what the ingredients are in the score function. One is the unique neighborhood. So it's the set of parity checks that talk to one and only one qubit. So for example, if I were to consider a parity check here, it talks to only that qubit in F, but it does not talk to any other qubit in F. So this orange set here represents the unique neighborhood. And RC, the complement of the suspicious parity checks, is the set that you can, is the set of parity checks that you can trust. These are not adjacent to qubits that you suspect have an error. Sorry, this animation, I'm not sure why two appeared at once, but this entire set was meant to be green. And what you're saying is that if you as a qubit, if you talk to very few people that I trust, then I don't trust you either. So there's a threshold here, it's H. And you're saying, if your friends are bad, I don't trust you either. And this is like a weighted score function to decide whether or not you trust that set F. And if it's below that threshold, then that set is going to get added to your envelope, and all of its friends are then going to get added to the suspicious set of suspicious parity checks. So I don't trust you, I don't trust your friends. And so then the set of suspicious parity checks is going to grow in every iteration past just the set of unsatisfied parity checks that we started with. Okay, so with that, let me also quickly compare the previous algorithms. When I talk about an erasure conversion algorithm, of course, the first one that comes to mind is union find. This was, in a similar spirit, an algorithm that converted poly errors into erasure type errors for the surface code. But this algorithm unfortunately doesn't directly generalize to hypergraph product codes. And Delphos, Beverland, and Lund found that it was unable to correct errors of weight up to the distance. It only corrects errors of weight up to d to the beta for some beta strictly less than 1. So in contrast, we can here we can achieve d to the beta. And the other algorithms to compare against, are flip. And there we find that we do better than the original version of flip, but not better than the iterations that came afterwards. It's unclear whether we do better than the iterations that came afterwards by Fawzi, Gropelli, and Leverrier. So with that, let me conclude just by leaving the summary and Outlook slides up and open for questions since I'm out of time. Thank you.
Yeah, so we actually have plenty of time for questions. 5 minutes. Go ahead.
Hey, can you deal with syndrome errors with this?
We don't know. I haven't checked, but I would be willing to bet yes, but I don't know is the real answer.
Oh, thanks.
Great talk.
Thank you.
So on the question of the adding in the erasure decoder to this, I mean, does Wiedemann's classical algorithm have an erasure decoder
Yes.
in it, and does that generalize?
Right. So it does not generalize, no. We have problems anytime we try and generalize a classical decoder. We run into some problems. And in the quantum setting, this hypergraph product that we consider, the Cartesian product of two graphs, is itself not a good expander. So therefore, you're not going to have every set is not guaranteed to have a unique neighborhood. And so consequently, the sorts of tricks that Wiedemann uses don't directly generalize to the quantum setting. So we need to be a little bit more clever when designing erasure decoding algorithms.
Thank you.
Thanks for the very nice talk. What is the essential element that makes this decoding works? Or equivalently, can you generalize this decoding procedure to some other codes other than hypergraph protocols? Is a similar requirement as the SSF, which requires expanding?
Right. Yes. So it does require expansion. Expansion is a crucial element. I think it would it should be able to work for the class of good codes with distance proportional to n. Sorry, what were the other parts of your question?
So is that like expansion the only requirement? So is that or like does it require extra things compared to say SSF decoder?
Right.
Or some
so our
flip
proof
decoder?
proceeds in two parts. One, to show that the envelope certainly covers the error, and the second part is that the envelope itself isn't too big, because a trivial envelope is to include all of the qubits. And the first part, we do use a product structure. So that is specific to hypergraph product codes and generalizations thereof. So I suspect some of the codes that you've just listed do have this structure. But if you come up with a new magical code tomorrow that's not product-ish, I don't know.
Okay, thank you.
Okay, yeah, go ahead.
Hi. So do you have any idea of like, can the envelope get too big? Do you have an idea of how optimal this growing process is?
Yeah, so we do have bounds on how large the envelope becomes. So if you're given an error of a certain size, we know that the envelope itself is going to be some constant multiple that depends on the parameters of the underlying graph times the size of the error. So it's not, so the size that it blows up is limited.
Okay, great. Thank you.
Okay, any further questions? If not, we can thank the speaker again.